One more question we can ask as we explore the concept of microevolution is, how can population remain at equilibrium? And so to answer the question, we have a set of 5 conditions established by Hardy and Weinberg, and the 5 conditions must be met altogether, not 1 out of 5 or 3 out of 5, even 4 out of 5. All 5 conditions must be met for a population to remain at equilibrium. And so these conditions are populations must be very large in terms of the numbers. If you were to press me for giving you a number, I would say, well, the population will have like maybe hundreds of thousands of members, and the population would have to have no gene flow, meaning that there's no new individuals coming in with new alleles. There are no members of the population leaving, taking away with them alleles that perhaps were only present among those that were about to leave. So no gene flow. Another condition is going to be that mutations are not going to be contributing new alleles to the population. Mutations will have to be just at the level of non-coding DNA. Mating would be random, meaning that all the members in the population are guaranteed to have a chance to mate. And when they mate, it's like they will have equal reproductive success, meaning that every member of the population contributes exactly the same number of offspring to the next generation. As we look at this list, one can immediately say, wait a moment, what population can do that? Perhaps you can find a population that meets 1 or 2 of these conditions, but not all 5. Let's see how populations are unlikely to meet all 5 of these conditions. Many populations in nature are going to be naturally small. For example, there's never been enough panda bears in Africa, in China, completely wrong continent. There's never been enough panda bears in China that number the same number of ants you have in the same place. And so some populations are naturally going to be smaller in number. Other populations are going to be larger. And when you have a population that is going to be small in number, it's going to be more likely to experience random changes in its gene pool. And those are going to be, those random changes in the gene pool in the population is going to be known as genetic drift. Genetic drift can be the result of a bottleneck event, or a bottleneck effect, as it is also known. Consider, for example, here in the coast of California, in the Pacific Ocean in the United States, there is going to be an animal that breeds there. It's going to be the elephant seals, like the ones you see pictured here in this illustration. And now I think I want to be using the highlighter mode. I think that's going to be more convenient for me right now. Not the highlighter, the laser pointer. So here we see these elephant seals that are in a beach where they are have gone through the process of mating. I can see a pup over here. I can see other young elephant seals also here in the sand. And so what happens with elephant seals? The populations of elephant seals in the west coast of the United States numbers at about, at most, about 20,000 breeding pairs. And so that is relatively a small number when you compare that to the number of rodents you can find in the same place, or lizards of a particular type. So what happens when there is an El Nino year in the Pacific Ocean is that most of the fish these animals are feeding on prefer colder waters. And so they move up higher towards the North Pole. And these animals, which cannot follow the fish because they are restricted to finding a beach to mate and to have their young, where they stay in California, there's going to be a limited amount of fish. And so the females, which need to go back to the ocean, feed on fish so they can continue making milk to feed the pups, are going to be suffering a great deal of stress. I'm talking about an El Nino year, and most of the fish these animals depend on have moved up north. And so what happens? There's going to be a great deal of mortality. Females will die, but especially the young, the pups, are going to die. And so what happens is that from one year to the next, in a population that is relatively small, you can see a change in the gene pool just because those that died perhaps had alleles that were rare and unique to them and not present among the survivors of that population. The founder effect is another interesting thing that happens when you have a small population. If something breaks up this small population, and imagine that there's a small number, even smaller number than the original population, moving to a new place, maybe with better conditions, those that move to that place may carry within them certain alleles that used to be in lower frequency before, but those founders that move to the place will be the only ones that are breeding. And so that allele or set of alleles that used to be at a low frequency will, in the next generation, show up with a greater frequency. And again, who can predict when a small population may fracture, splinter into two different groups, or when a natural catastrophe will come and wipe out most of the members of a small population? Nobody can predict. So that's the random nature of the changes that can be taking place here. So remember, bottleneck events and founder effect are going to be how in a small population there can be from one moment to the next a random change in the frequency of alleles. Another type of source for changes in the gene pool of a population is going to be migration dynamics. Hardy and Weinberg said there should be no gene flow. However, we know that for most populations, you can imagine, count plants, animals, bacteria, fungi, through spore in the case of fungi, through pollen in the case of plants or seeds. There's going to be a movement of genetic material from one place to another, or individuals from one place to another. When the movement is in to the population, we'll call that immigration. When the movement is out, we're going to be calling that emigration. And so that can change frequencies of alleles in a population. Mutations, we know that they happen, and on rare occasions, but nevertheless they do happen. Mutations can produce a new allele. And those new alleles at first may be neutral. They don't have to be beneficial. The allele doesn't have to be harmful. If it becomes beneficial, then it has the potential for becoming an adaptation. Look, for example, at what I have here on this slide. These are snakes I have personally surveyed in Southern California when I was in grad school, and I will go into the grasslands of Southern California to try to assess which places have this particular species. This is a California king snake, and what you can find is that a single parent, single female, can produce both types of offspring. The offspring that has the stripes and the offspring that has the rings. Now, if you wanted to ask me, hey, Mr. Murcia, you study these snakes, is there one that is one color pattern that is more successful than another one? And I'll tell you, nobody knows. They're both present at seemingly equal frequencies, but if something happened in the environment and perhaps a type of vegetation made it better, easier for the ones with rings to hide, to blend, and avoid predators, it could be that this variation and this type of coloration becomes an adaptation, becomes an advantage for survival, and it could be that these snakes that are more easily spotted by predators will be the ones that disappear. We don't know. So this type of phenomenon where mutations give rise to two different forms in a population, we call that polymorphism. Poly simply means many, morph means forms, many forms. In this case, we have two different forms, same snake, same species. These two could be siblings. It's possible, and yet they look so different. What is the reason? Well, the reason is going to be a mutation produced these two variations in the pattern of the coloration of the scales on these reptiles. So now we've accounted for three possible causes for microevolution. Small populations can be susceptible to genetic drift. There can be migration, emigration, going out, or immigration coming in. Mutations can also produce new alleles that will change the gene pool of a population. What else is there? Mating. Mating especially in animals, it's not going to be random. There's going to be mate selection, and I will be addressing this at a different moment, perhaps in class or a video. Why or how are females usually the ones that choose which male is worthy of fathering her offspring? So what are the traits that one member of one species may prefer? Nobody can predict that. I mean, you just have to observe the breeding behaviors of animals to be able to decide, well, this is a trait that is being selected. In the case of peacocks, I love peacocks. They are beautiful animals, but they are also interesting in their behaviors. Females have a way of assessing visually the number of eye spots on the tail feathers of a peacock. And the males that are the more successful are going to be those with the longest tail feathers and with the greatest number of eye spots. And so does that make them attractive? Is that a sign of good genes? Or maybe a male that is old enough to have such beautiful plumage? We don't know for sure, but those are all hypotheses that could be used for explanation. And so what happens is that because mating is not random, natural selection will work. And here, I want to make another, give you another synonym for natural selection. Before I had told you that descent with modification, well, that's what we call now natural selection. But another synonym we have for natural selection is going to be differential reproduction. We've seen this term before. We saw it when we were looking at how natural selection happens. I will remind you, differential reproduction means that in a population, some members of the population produce larger numbers of offspring, you remembered. Others are going to be producing smaller numbers of offspring, and some are going to be producing no offspring whatsoever. Why do I have this illustration with lions? Well, in Africa, lions are going to have a social hierarchy. And when you look at a lion pride, there's going to be an alpha male. There may be other males. Well, there will be the juveniles. There will be the male offspring for that male. And the rest of the members of the pride are going to be females. Now, something interesting is happening in Africa. In some parts of the continent, the weather is getting so hot that having a mane can be stressful. And so males, like this one over here, which doesn't have as big a mane as other males may have in other parts of Africa, is actually what females prefer. And so this male that has the right characteristics a female wants is going to be the one that takes, control of a pride, perhaps is going to be the strongest one that can kick out all of the other males or defeat a previously ruling male in a pride. And for a number of years, this male is going to be the only one that will be producing offspring. What happens to males that don't ever develop a body size or characteristics that are capable of making that male compete and take control of a pride? Many of those males will never mate, and they will never leave any descendants. And so natural selection through the process of differential reproduction is also going to lead to changes in the gene pool of a population. Frequencies of alleles will be shifting in favor of the characteristics of those that are successfully mating. The characteristics of the future generations will be those that are passed by the more successful individuals to their descendants. And I will conclude with this exploration of causes for microevolution.